Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our work is the title Metric Completion with Noisy Site Information. I'm Kayang Chan, and this work is the joint work with Jory Shea and Inderjit Dillon from UT Austin. So the goal of this work is trying to exploit the site information for metric completion. So for example, if we consider Netflix problem where we want to use the user rating history to make a prediction on the user movie ratings, and the standard way is to use the metric completion where we can learn the low-rank metrics which capture the observed ratings, and we can also use the completing metrics to make a prediction. But in some circumstances, we also given some additional information like the row feature, like user feature in this case, or the movie feature in this case. Then we can utilize these kinds of the information to make a better prediction. So for example, there is a model called IMZ, which you can incorporate the feature information into your prediction. And the question here is that how much can the site information help to the metric completion problem? So to highlight our work, we observed that the previous results, for example, IMC, they've showed that the preferred features are very useful, but for general kinds of features, they actually cannot guarantee the recovery of the underlying metrics. So compared to them, we proposed a new model which we leverage the feature information and the observation information better so that we can prove that using the good quality of the features, it is enough for the, to prove the features are useful. And moreover, we can guarantee the general feature can also be used in our model. So to highlight this idea, consider that here the yellow box here are the matrices that can be recovered by the metric completion. So if we are given the site information like X and Y as the features, then we can divide the space here to 4 subspaces. And the previous results shows that metrics like R1 can be recovered effectively if we are given the X and Y. But for other metrics like R2 to R5, actually it fails to recover. So we observed that for example here, R3 to R5, X and Y still consist of like sufficient information of the underlying metrics. So we basically handle these kinds of the instances and to propose a new model to handle the useful features. So if you are very interested in our works, you can come to our booth 55. Thanks.
Hello, the title of this talk is Fast and Guaranteed Tensor Decomposition While Sketching. I'm Yining, and this is a joint work with Xiaoyu, Alex, and Anima. So we consider the symmetric tensor CP decomposition problem in this work. For an input tensor T of dimension n, the goal is to find k eigenvalue and eigenvector pairs, lambda and ui, so that the reconstructed low-rank tensor approximates the original data tensor T in Frobenius norm. So this problem has wide applications in data mining and more recently in parameter recovery for latent variable models. One popular choice for the decomposition problem is through the tensor power iteration method. At each iteration, we compute a normalized tensor multilinear form based on the vector of the last iteration. It can be shown that under mild conditions, this tensor power iteration procedure will converge to the true underlying vector with high probability. However, this method is not often used in practice because it is computationally intensive. For example, if the original tensor T has n dimensions, you would require n cube operations to perform each iteration. This is prohibitively slow for most large-scale data applications. So in this work, we propose an accelerated tensor power iteration method based on the idea of sketching. So the general idea is to first pre-compute a compressed sketch of the original tensor T. Afterwards, each tensor multilinear form can be approximately computed in near linear time by using the trick of fast Fourier transform. As a result, the time complexity of each tensor power iteration is reduced from n cubed to n plus b log b, where b is the length of the sketch and is typically much smaller than n cubed. We also apply our proposed method on some real-world machine learning applications, such as topic modeling. In this problem, we want to recover k latent topic distributions from unlabeled documents. So we compare the negative log likelihood and running time of our proposed method with collapsed Gibbs sampling, and we show that a hybrid approach will outperform Gibbs sampling in terms of both document modeling and running time. So for more information, please come to our poster. Thank you.
Hi, I'm Akshay, and this is work with Joa Freund at UC San Diego. We give an algorithm to tackle the central question of semi-supervised learning, which is how do you sort of generically and efficiently improve upon fully supervised, let's say, binary classification using unlabeled data. So you might do binary classification by first trying a few algorithms, say at an SVM, decision tree, DeepNet, using the labeled information to estimate their errors, and then after that, using that information to decide how to predict, maybe by picking the best single classifier, taking some sort of vote, or so forth. To this, we add unlabeled information in the form of the ensemble predictions on unlabeled data. So we get to poll the ensemble. And what we give here is an algorithm which, when viewed as a black box, takes the labeled information in the form of these estimated errors and the unlabeled information in the form of ensemble predictions, and spits out predictions on the unlabeled data. Now these predictions, these y-hats, have error which is at most that of any single classifier in the ensemble. So this is a sort of safe thing to do, and the paper is mostly empirical. But let me get into what the algorithm is inside the black box. It's an efficient algorithm that processes the unlabeled data through stochastic gradient descent, basically. So you only need to handle one unlabeled point at a time. And it consists of a learning algorithm and a prediction rule. The learning algorithm is a convex optimization, which is this gradient descent, as I said. You get from it a non-negative weight vector over the classifiers that you input, the SVM, decision tree, DeepNet, etc. The prediction procedure on each unlabeled test example takes a linear combination using those learned weights of the ensemble predictions on that test point and runs it through a rectified linear unit to generate the binary prediction on that test point. So you can call it a neuron with learned weight sigma. The interesting thing about this is it's actually a lot stronger guarantee than I said on the previous slide. In fact, no predictor at all has a better worst-case error guarantee given the ensemble errors and the unlabeled data. And most of our paper is empirical, running this algorithm on random forests and showing that basically given an ensemble of the trees in the random forest, we can outperform random forests pretty consistently and significantly. So for more, please come and see our poster, number 38. Thank you.
Hi, I'm TK Huang from Microsoft Research New York. This is joint work with Daniel Su from Columbia, Alec Agarwal, John Lamford, and Rob Shapiri from MSR New York. So we consider streaming active learning. In every round, the learning algorithm receives a new example X, sampled IID from some source. And on the spot, the algorithm has to decide whether it wants the label or not. If it does, it sends the example to some labeler, gets its label back. Otherwise, the algorithm does nothing, just skips and proceeds to the next example. So the goal is to maximize classifier accuracy per label query. And the important question is, how do we make the query decision? So in this work, we developed a new algorithm, active cover. This algorithm uses efficient reduction to supervised learning. So it can be used with, for example, SVMs, decision trees, DeepNets, or whatever supervised learning algorithm you like. And the important thing is the query decision is randomized. So on a new example X, the algorithm only queries its label with a certain probability. And our main contribution is we use a novel query probability obtained by solving an optimization problem. As a result, the query probability has the following form. So suppose we choose a set of classifiers H, say linear classifiers. The query probability is an increasing function of a weighted count of all classifiers in H that disagree with the ERM classifier on X. The ERM classifier is the one that minimizes the training error on all the data the algorithm has seen so far. Both the exact functional form and the weights are learned through optimization. A nice property about this is that more disagreement on X means a higher chance of querying its label. We showed that this new algorithm provably learns an accurate classifier while making fewer label queries than all previous efficient agnostic active learning algorithms. We performed an extensive empirical study on 22 classification datasets. For more details, please come to our poster number 61. Thanks.
My name is Anna Choromanska. I'm from Courant Institute at NYU, and this is a joint work with John Langford from Microsoft. This work focuses on the multi-class classification problem with a very large number of classes. Consider a simple example of this problem. Imagine I give you a bunch of images, and I ask you to recognize faces on these images. This is clearly a multi-class classification problem, in fact with billions of unique labels. Most algorithmic approaches for multi-class classification have a linear running time in the label complexity. The gain of using logarithmic rather than linear running time approach is negligible when the number of classes is small, like 10 or 100, but becomes significant when the number of classes is much larger. So for instance, at million classes, the speed up is of a factor of 50,000. This gain is huge and cannot be easily ignored. We attack the multi-class classification problem by reducing it to a binary classification problem organized in a tree. The data splits in tree nodes are done by maximizing a new splitting criterion that was not considered in the decision tree literature before. Maximizing this new objective is essentially equivalent with maximizing the dependence between the left or right split and the label. We judge the quality of the entire tree using Shannon entropy. We obtained the boosting theorem that relies on the weak hypothesis assumptions and shows the number of splits that is required to reduce tree entropy below an arbitrary threshold epsilon. This guarantee under favorable conditions directly implies logarithmic training and testing running time. Here we are comparing the performance of our algorithm that we call a long tree with the common linear running time approach one against all. On the left plot, we show the performance of both algorithms when varying the number of classes in the classification problem, and where long tree is constrained to use the same representational complexity as one against all, and one against all is constrained to use the same running time as long tree by data truncation. Clearly, as the number of classes increases, the problem becomes harder and our approach becomes dominant. On the right plot, we are showing on the logarithmic scale the ratio of the per example test time for one against all and the long tree. The plot captures nearly linear dependence and empirically confirms the logarithmic running time of our approach. So to give you an example, on the full ImageNet dataset, our algorithm performs predictions in about half millisecond. So if you would like to learn more about this approach, please see poster number 37. Thank you for your attention.
Right, so hi everyone, I'm Brendan and this is joint work with both Aditya Menon and Bob Williamson. Sadly, neither Aditya nor Bob could make it to NIPS this year, but don't worry, if you like the paper, I'm more than happy to take all of the credit. If you don't like the paper, and I mean, I don't know why you would, wouldn't, that's what I meant to say. It was really all Aditya's fault, and Bob and I really tried hard to stop him. So in the normal theoretical analysis of binary classification algorithms, we normally make the very strong assumption that the training set and the test set come from the same distribution. Now this is rarely, if ever, the case, and in the paper we consider possibly the simplest deviation away from this well-studied model, and that is given by learning with symmetric label noise. So we assume that the training set has had its labels flipped with some constant probability, and this is on top of any noise in the underlying pattern. So it turns out that naive approaches to this problem, so for example, just pretending there isn't any noise at all and running, say, a support vector machine on the corrupted training set, can lead to substantially suboptimal performance. And in fact, this is true of a large variety of convex approaches to the problem. So this has led to the folk belief that you need to resort to a non-convex loss function in order to avoid the effects of label noise. So what we find is that this isn't actually true at all, and in fact, to avoid the effects of symmetric label noise, you don't need to resort to these complicated non-convex procedures at all. In fact, all you need to do is take the hinge loss function from support vector machines, unhinge it, and use the linear loss function instead. So the linear loss function is provably robust to the effects of symmetric label noise. And in fact, in a certain technical sense, it is the only convex loss function with this property. So the minimization of the linear loss function enjoys many of the same theoretical consistency properties for learning binary classifiers as minimizing the hinge loss function. And furthermore, for the case of linear function classes, performing this minimization is remarkably easy. So as a sort of a one-line summary of the paper, and with the sincerest of apologies to Wild, while the truth is really pure, it can be simple, and if any of this has piqued your interest, then please come see me at the poster, and I'd be more than happy to answer any questions that you may have. Right, catch you, everyone.
Hi, my name is Nikhil, and I'll be talking about collaborative filtering applications with graph information. And this is joint work with Shangfu Yu, Pradeep Ravikumar, and Inderjeet Dhillon from UT Austin. So consider the standard matrix completion problem, where you have a partially observed matrix with just a few entries, and the goal is to figure out what the rest of the entries are. But also assume that there are graphs defined on both the rows and columns of the matrix. So in the case of collaborative filtering or recommender systems, this could be like a social network among users, or like a co-purchasing graph on the items. In the case of large-scale multi-label learning problems, the rows would just correspond to data samples, but then there would be the labels would correspond to the columns of the matrix, and then there can be a graph on the labels depending on what labels are correlated with each other. In gene-disease association studies, you could have a gene-gene interaction network or a comorbidity network on the diseases. And so this is a problem that comes up in a large number of applications. And the questions we want to answer is, how can we efficiently incorporate this additional graph information in making predictions in our scenario? And in doing so, what is the price we pay? What is the sort of statistical and computational trade-offs that you can show that lets us solve this problem? So in this paper, we first show that you can, in fact, incorporate this information in a fairly nice manner. We appeal to the notion of embedding objects on graphs and propose a nice regularization framework. We then propose a scalable alternating minimization algorithm, which achieves about 1.5 to 2 orders of magnitude speed up over stochastic gradient methods on fairly large data sets. Like the figure there shows one with about 16 million observations. And then finally, we show that we can actually write this as a simple convex optimization program. And in doing so, that lets us prove some nice statistical consistency guarantees for the method. And then you can see that the sample complexity is actually lower than what you would get if you just solve the standard nuclear norm regularized program. There's also a workshop on time series where we extend this to large-scale time series applications. You're free to check that out. For more information, comments, questions, please visit our poster, number 62. Thanks.
So this has been an extraordinary NIPS, a very special year. We've had a record 3,800 attendees to both the conference and the workshops. And we still have more to come. We want to, on behalf of the NIPS Foundation, we want to give thanks to the general chairs. Running a big meeting like this has many moving parts, and if you don't watch them, things can really fly off in funny directions. But Karina Cortez and Neil Lawrence did a terrific job last year with the program, and this year with the general chair. Let's thank them for their service. Now, this year's record number of submissions and the extraordinary number of reviews, over 10,000 reviews, sets the bar very high. So Dan Lee and Masashi Sugiyama, thank you so much. Without you, we wouldn't have had such a great meeting. Thank you. Now, the conference hasn't finished yet. In fact, we have a poster session coming up, and then, as you know, there's going to be a symposia, which is a new event that is occurring this year, this afternoon starting at 3. But we do want to make an announcement for the next NIPS meeting, which will take place next year in Europe, Barcelona. And we're very pleased that our program chairs for next year, Isabelle Guillon and Ulrike von Luxburg, have agreed to take on that task. Thank you so much, and they have a few words to tell us about next year.
Yeah, so we're really excited and also a bit scared of taking on this job. I just want to make 2 announcements at this time. The submission deadline is going to be earlier than this year. It's going to like all the decision procedures are going to move 2 weeks in advance, so be prepared to have your paper ready in May 20. And we also try something new where all authors who submit a paper are requested to also serve as reviewers. So we will have normal reviewers, but we will also request authors of papers to review a paper. So if you want to submit a paper, please be prepared to also be a reviewer for our conference. And all the other changes we will decide on during the next year, and you will learn them on the fly. Thank you.
We hope to see you all in Barcelona, and thank you for coming so numerous. Tell your friends to submit more papers. We're all ready to take the big load.
By the way, in case you were wondering, we're not going to let you review your own paper, okay? So, this is really exciting, and I'm really pleased to say that we're going to continue on. This is going in new directions that I would have never even imagined, even 10 years ago. So thanks to all the wonderful talks, and thanks for all the posters. It's been a wonderful year. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.